So next I'll be introducing the NumPy package and this super useful new object type called the array. So NumPy is what's known as a package, or alternatively a module or a library, and it stands for Numeric Python. So you might imagine packages allow us to go beyond the core functions of Python so that in this case we can do a lot more useful things with numbers. But first we have to tell Python to load this package. We do that using this import statement, which says import NumPy as NP. What that means is make all the functions in this package NumPy available in my code. And I want to refer to those functions using this shortcut NP. You can call the shortcut anything. You could also say, import NumPy as Seattle, but that would be chaos, so we don't do that. And technically, you don't need a shortcut at all. You could just say import NumPy. But since we refer to this package many, many times, NP is nice because it's short. So here we've imported NumPy as NP. Very briefly, packages like NumPy are usually developed by a large community of volunteers, and they're continually adding new features, fixing bugs, putting out new releases. So sometimes it's helpful to know the version of the package that we're working with, and this is how you check. You print np dot underscore underscore version underscore underscore. And notice we use that shortcut np. And here we see that Google Colab has installed version 1.18.5. Okay, so the whole world of NumPy revolves around an object type called an array. And you can think of an array like as like a supercharged list. Its official name is the ndarray for n-dimensional, where n could be 1 for a 1D array, 2 for a 2D array, and so on for higher dimensional arrays. And you'll learn more about that in the next lesson, but here we're going to focus on 1D arrays, like this one, 5, 6, 7, 8. We define the array by taking this list, 5, 6, 7, 8, and giving it as an argument to NumPy's array function, which again we access using the shortcut np. So at this point, you're probably wondering, what makes an array different from a list? But in many ways, lists and arrays are not all that different. Both are mutable, meaning that unlike tuples, you can change their values using indexing. So here we're changing the first index of numbers to 13. So we get, instead of 5, 6, 7, 8, we get 5, 13, 7, 8. And both are compatible with the indexing and slicing commands that we learned in lesson 3. So here we're slicing numbers from the third to last value onwards to the end, which gives us just 13, 7, 8. And like lists, arrays are iterable, so you can iterate over them in a for loop like this one. Both arrays and a list have lengths, which, as you saw before, you can check using the len function. And for both of them, you can also check membership using the keywords in and not in. So for example, 13 in numbers evaluates to true, while 14 in numbers is false because 14 is not in numbers. But there are some major differences. Lists can hold more than one object type, as you saw before, a mix of numbers, strings, even sublists. Arrays, on the other hand, can only hold a single object type. And you can check that type using .dtype, which says here, if you run that, int 64. That's basically an integer. You can also change the type of an array using the .asType function, as we've done here, converting numbers into an array of strings. Another difference. Lists are very slow when it comes to big data sets, so most of the time we try to avoid them. In contrast, NumPy arrays are built for big data, so they're computationally fast, and they take up as little memory as possible. Some more differences. In Python, you can write numbers in scientific notation, and you do that using the letter E. So like this, 3.5 E9 is 3.5 billion. Now, this is a small difference, but when you fill a list with numbers in scientific notation, it gets lost. On the other hand, NumPy arrays preserve scientific notation. This next one is a bigger difference. Hopefully you remember that there are these list functions Katie introduced in lesson 3. And with lists, you can extend, insert, del, and reverse. Well, NumPy has similar functions to those arrays, those array functions. Those 4 arrays. And those are append, insert, delete, and flip. Though it doesn't have a remove or pop function. But for these similar functions, the syntax is different. So for list, you'd be writing the list numbers dot append, and then what you're adding as the argument. But for arrays, the target array becomes an argument, followed by a second argument, the list or array that you're adding. And also, appending to a list modifies the list in place. On the other hand, appending to an array does not happen in place. So you have to save that result into a variable if you want to do something with it. And that's the syntax here. And lastly, you should know that the append function for arrays is more like the extend function for lists, and that the list function, the list version of append, creates this sort of annoying subarray when you add multiple values, while NumPy's append doesn't. So again, NumPy's append function is like extending a list. How do you convert between lists and arrays? Well, you already know the syntax to turn a list into an array. But to go from an array to a list, you have 2 options that both work. There's NumPy's .toList function, and there's also Python's built-in list function. Different syntax, same result. Okay, and then there's this last difference, and this one is a big deal. So remember how when you add 2 lists together, that concatenates them. It joins them together into one longer list. Well, with NumPy arrays, when you add them together, they actually get added together, like mathematically added. And again, this is a big deal. You previously had to do this sort of addition using for loops and indexing. It was cumbersome, but now it's going to become so much easier with arrays. And that brings us to arithmetic operations with arrays. I think this slide is probably the most important one of this entire lesson. So if you remember from lesson 2, we have these 7 arithmetic operators that we've been using on numbers in Python. Well, it turns out we can use them on arrays as well. So that includes taking 2 or more arrays and adding, subtracting, multiplying them together. And when you do this, it happens element-wise, meaning that the 0th element of A gets added to the 0th element of B to give you the 0th element of the result, and so on for other elements. So in this case, for A plus B, you get the sum of the index 0 elements, which is 6, the sum of the index 1 element, which is 8, the sum of the index 2 elements, 10, and the sum of the index 3 elements, 12. Subtraction, multiplication, these other operators, they work the same way. Not only can arrays do math with each other, but you can also add, subtract, etc., arrays and numbers. For instance, A plus 10, it adds 10 to every element of A, and it gives you a new array, 11, 12, 13, 14. Same deal for multiplication, division, exponentiation, etc. So for A squared here, that gives you 1, 4, 9, 16. The values of A each squared. So overall, being able to do math easily with arrays is going to open up a whole world of possibilities that were just too difficult to do with lists. Just a word of caution here. If you try to perform element-wise arithmetic between 2 arrays of different lengths, like these X and Y arrays, you're going to get an error. And this is NumPy basically saying, hey, you can't use that plus operator to add an array of length 3 to an array of length 5. Hopefully that makes sense. Next thing. So guess what? You can also do element-wise logical comparisons using these familiar operators here. So here in this first example, you're comparing 2 arrays, checking which elements of those 2 arrays, U and V, are identical, which gives false, true, false, false, saying that only this element at index 1, only the elements at index 1 are identical, those elements being both the number 2. You can also compare an array with a number. For instance, v less than or equal to 4 yields true, 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 false, which says that the first 3 elements are indeed less than or equal to 4, but that final one is not. Now here's something different. If you want to compare 2 Boolean arrays like bool1 and bool2 here, there's a bit of a quirk. NumPy won't let you use the logical keywords and or that you could with numbers. You can't write, for instance, bool1 or bool2. It's not going to work. Instead, with arrays, you have to use these functions logical and logical or, as shown here. And that gives you these element-wise comparisons. Okay, so this last thing is so useful. NumPy gives you some new, very clever indexing options. So say you have this array called v, which is 10, 11, 12, 13. You can still access a single value using a single index, like you did with lists, v brackets 3, and that gives the 0th, 1st, 2nd, 3rd element, which is 13. But now you also have the option of selecting multiple values using a list of multiple indices. So here we have these outer brackets to say that we're indexing, and inside our inner brackets to say that this is a list, index 2, index 3. And indexing using that list gives us elements 2 and 3, which are 12 and 13. This next one is pretty cool. You can actually index using logical conditions. So say you want all the values in the array called v that are greater than or equal to 12. Well, all you do is put that logical condition inside the indexing brackets, and you get back the elements 12 and 13 because those were the ones that were greater than or equal to 12. So you can see over here. And what's really happening when you do that is that v greater than or equal to 12 evaluated to this Boolean array, false, false, true, true, like you saw in the previous slide. And that Boolean array is being used to index into the array v, saying, no, we don't want the first 2 elements, but yes, we do want the last 2 elements. Okay, so that's how you get values when you know the exact indices, or you have a sense of what you're looking for and you can write a Boolean condition for it. But what if you already know the values that you're looking for, but you want to look up the indices of those values? Well, then you use NumPy's where function, which takes a Boolean condition as the argument. For example, if you want to write, where are the values of v greater than or equal to 12? NumPy will tell you, well, they're at indices 2 and 3. Now just be aware that this function gives you this result in this weird tuple format, and you have to unpack it by indexing into that result using bracket 0. And that will give you just those indices that you were looking for. That's it for this segment, and see you in the next one.